A wind converter can be considered as a mature component within wind turbine generators. However, a significant number of failures are still assigned to wind converters. A wind converter is responsible of the energy conversion from the rotating electrical machine to the electrical grid. It is a static power conversion system. That means that it has not moving parts, and this makes not easy to prognose a problem. The best practices in prognosis in wind turbines cannot be applied to this component. However, the industry, wind turbine manufacturers, are aiming to increase wind converter reliability, and that's the aim and goal of WindTrust, a research and development project that aims improving wind converter reliability. Two wind industry leaders, Gamesa Electric, a wind converter manufacturer, and Semicron, a semiconductor manufacturer, have worked together to have the new era of wind converters. A large analysis of wind turbines errors has concluded that there are two lines to have a reliable wind converter. The first line is related to the power stack, semiconductor power stack. In WindTrust, we have developed a new semiconductor power stack with 4 features. The first one is a high power dense component that is built on big build blocks that has less components. The number of failures is independent of the elements and the number of blocks. So the less number of blocks, the less failures. Besides, this component has less thermal stress due to the high cycling capabilities with a mechanical design that reduces the thermal stress. It's designed to withstand high polluted system with high condensation system that is very normal in wind industry. Also, we include a prognosis real-time algorithm that tells you whenever the IGBT is going to fail. So the 4 issues is inside this power stack that is inside the wind converter. The second line of work is the converter concept design. We have designed a modular converter with different areas where we can separate thermal stress. So the components inside are with a better cooling operating at a lower temperature that raises availability and thermal performance. The second point is reducing the electronic parts. By having just one single control board, we reduce the number of elements and we also raise reliability. This together with a maintenance-oriented concept that enables technicians just access to the parts where the problem is, we assure that the time to repair is also low. Summarizing, WindTrust has enabled a new generation of wind converters with better performance, higher reliability, and better maintainability that gives a new era for wind converters.
Offshore wind energy has many advantages. Once you go to the sea, you're offered nearly unlimited space for installing very big and large turbines, and you're offered very stable and reliable wind conditions. You're also not restricted by any noise regulations or height restrictions or the like, and therefore you can build nearly as big turbines as you want. However, also because the turbines are becoming bigger and bigger with longer and longer blades, also wear and tear has become an even bigger problem than earlier. I mean, in fact, we have found out that rain erosion on the leading edge of the blades is actually the dominant failure of the blades, and repairs are offshore very expensive. So in fact, we have within the WindTrust project been searching a lot for durable materials for actually this leading edge protection system, and we have found a polyurethane coating which has actually proven to have 5 times the lifetime of the conventional tape solution. And that actually means that the overall levelized cost of energy will decrease quite a lot, because if you don't have to go there to maintain the leading edge and do expensive repairs, that will really cut off a lot of the costs. So we continue to strive for finding very durable materials, and this new coating is just the first step. We'll go even further and try to enhance all the properties and costs for protecting the blade more. And but it is also a very big investment, and you need to protect that during the entire lifetime, which is also already now up to 25 years, and it will become 30 years over time.
This is the leading edge of a wind turbine blade. This is exposed to extreme conditions during a design life of 20 years. It's operating at close to 300 kilometers an hour, being hit by multiple rain droplets and exposed to extreme wear. This affects the aerodynamics of the blade and thereby also the annual energy production. Here in Lunderskov, we've been developing and testing materials for a long time now, and one of these facilities that we now have is a rain erosion tester. This rain erosion tester gives us the capability of simulating the conditions that we have in real life. These real life conditions we try to monitor and validate through a rigorous test programs. We monitor the droplet size, the fall height, we monitor the tip speed, the average temperature of the rain, the room temperature, and we test multiple materials in order for them to withstand the extreme conditions that we see in the field that we have today. To combat erosion, currently there's a lack of design standards for rain erosion. Part of the work that we're doing is a collaborative initiative with different companies, and on a broader scale within the EU as well. We define how to do rain erosion testing. We also define and want to predict how rain erosion testing can be adapted into the real life conditions, and thereby calculate the expected lifetime of the different solutions. All of these solutions are critical in obtaining the lowest possible cost of energy for wind turbines. The key aspect of the rigorous test programs we're running, the aim for providing design standards for the industry is in the end to meet the very stringent cost on wind energy. We need to be on par with oil and gas, coal energy, and thereby provide an efficient energy source with the lowest cost of energy. So in the end, in order to achieve the most out of our efforts in rain erosion testing and also the development of new materials, we aim to combat the multiple impacts of the rain droplets as we see here today, and thereby increase the profitability of wind energy.
Noise is a very important variable for the wind turbines during its design, because at last a lot of locations could be limited by acoustic restrictions due to neighborhood proximity, population, and so on. So in the WindTrust project, we have developed kind of devices located in the trailing edge of the blades, mainly in the outer part of it, that tries to reduce these sources that produce this kind of aerodynamic noise that is dominant over the other. And the way they work is that the pressure waves in the airfoils going towards the trailing edge are the way they interact with the trailing edge is modified by these devices, because the angle of incidence of this pressure wave is not normal. So the way they interact is reducing the acoustic impedance, and this reduces the intensity of the acoustic emission of the wind turbine. So this helps to improve the way the wind turbines can be just installed and fulfilling the restrictions we have in the locations. We have by now designed and installed these devices in the G90 wind turbine with a 78 meters height tower, and the results goes from 2 dBs more or less noise reduction. Okay, and for this model we have also designed this kind of devices for other blade models and tested in acoustic wind tunnel, because it's very important to take into account that these devices design is not general. You have to design these devices according to the blade geometry, your blade aerodynamics. It is specific, so that you can obtain this benefit in noise reduction. So this design combines high fidelity calculation by CFD and advanced methods, but also wind tunnel testing, mainly aeroacoustic testing. And we have, as I say, designed this kind of devices also for other models. And the idea is to check the potential noise reduction for other these aerodynamics. This noise reduction you have in a model allows you the possibility, for example, to increase the rotor diameter. That is very linked to the noise emission, because at last you can go to the same overall noise emission, but with a larger diameter, and that allows you improving the energy production.